So the second approach is to try to design channel selection filter in analog domain. Okay, to understand challenges in designing a channel selection filter, so let me show the spectrum of input signal along with signals in the other channels. So here we are concerned with only signal in one band, which has multiple channels. And let's say the desired signal is present in one of these channels. So the channel selection filter, as we can see, has to select only this narrow band of frequency while rejecting other frequencies. It requires the filter to be really sharp. So you can see so this roll off has to be very steep, and compared to the band select filter, here we can see that this has to be even sharper. This requires filter to be roll off. Okay, and in turn, this sharp roll off requires filters to design with higher order. Higher order means it needs to have lot more poles to help in achieving such a sharp attenuation. Okay. Normally, when we try to design a higher order filter, it requires more storage elements, and overall the filter becomes really bulky. And this is not the only requirement. If you look carefully, you can easily see that this channel also has to be tunable, because sometimes your desired signal may be present in this channel, sometimes it may be present in another channel. So depending on the overall requirement, the desired signals can be present in any one of the channel, and you want this filter response to be tunable. The two really difficult requirement for this filter coming together. We want tunability as well as high order. So in general, it is not a very trivial task, and design of such filters can itself become very bulky. Many times it may be even impossible to design in a given IC technology. So what is being done is, instead of trying to make the filter response to be tunable, what if you can somehow make the signal itself to move in frequency domain? So if you can achieve that, it is possible to change the channel which is going to be selected by the filter without requiring a tunable high order channel select filter. Okay, you may still require basically maybe a sharp roll off, but now the requirement has been that it need to be just a fixed filter with sharp roll off. So conclusion is difficult to realize a high order filter with tunable frequency response. What we can do, make the input signal frequency tunable, okay, while using a fixed filter or channel selection. The signal frequency is tunable and the filter is fixed. So I hope the motivation is clear to all of you. Now the next step is just to find out how to achieve this. So here we are talking about shifting the frequency of the input signal. So this part we have already seen earlier in the context of a transmitter design. If you are given an input signal and we want to shift its frequency, we can make use of mixing operation, which we have already seen, where we multiply the input signal with a signal coming out of an oscillator. Say this signal is at F. F. Signal is coming out of oscillator is at FLO. We know that the output frequencies are going to be FRF plus FLO and FRF minus FLO. So, as to look at the spectrum, see the signal at centered at frequency FRF. FLO says somewhere here. So the mixing operation is going to give rise to two signals. Okay, so one is going to be at a lower frequency here, and then there will be another part at higher frequency. So we're here. Exactly. We're also going to get and this center frequency here we can see is going to be FRF minus FLO, whereas this center frequency here is going to be FLO plus FRF. Now in this scenario, if you want to do channel selection, we can put a fixed filter which will select one of the required channel, let's say, and this lower frequency. And once we put a filter here, automatically this higher frequency component which is generated out of this mixing operation will be filtered out. So many times you prefer to design a channel, a fixed filter at a lower frequency, because the design itself will be much easier, and you will also require a much lower order filter as compared to designing a channel select filter at a high frequency. So next step is to add a filter here, which is always selecting the frequency around a given which is always selecting signal around a given frequency. So this fixed filter will be selecting always something around here. And if you want to make this filtering to be tunable in frequency domain, what we can do, we can change the LO frequency so as to move the down converted signal as a result of this mixing operation, so as to allow the required channel to always pass through this fixed filter. So the next block and the output of this mixer is going to be again a band pass filter which is going to select the required channel. This is our channel select filter. Now we can see that this ADC is handling a signal which is at much lower frequency compared to the input signal frequency. So the ADC design has also become simpler. So this architecture is helping us in simplifying ADC design as well as in the design of a channel select filter. So we are achieving two operations here. One is we are able to get frequency down conversion, and as a result of this frequency down conversion, ADC design is also simplified. Of course, in addition to simplifying the design of channel select filter. It not be high order as expected. Because for the same spacing between the two channels, now the roll off as compared to the center frequency is much shallower compared to what we are requiring a higher center frequency. So you gain in two ways. Now if we try to draw the complete architecture, Here it looks like you have got an antenna, band select filter. The next stage we are adding a hello. And if you want to make this channel selection to be tunable, hello has to be also tunable. Its frequency should be tunable. Hello. With tunable frequency. This output is again passed through. Right now we are showing it as a band pass filter, which is using channel selection. This is a channel select filter. And we are adding a VGA to bring the signal into the utilizing the full dynamic range of the input of the ADC. Which is now running at a much smaller sampling rate compared to the previous case. So this architecture, where you start with a signal at a frequency FRF, and then after mixing and filtering, we obtain intermediate frequency, which is going to be at the difference frequency of the RF signal and the FLO, which is later amplified and fed to an ADC. So such an architecture is also called as heterodyne architecture, or in this case, it's a receiver. We call it heterodyne receiver. Heterodyne means we are using more than one frequency. So here we can see that we start with some FRF and there is an intermediate frequency FIF. That's how this name has come, heterodyne. This frequency is called as intermediate frequency. Now we can see that there is a receiver which looks like can perform the job satisfactorily. And to further understand what may be the difficulties or challenges in this architecture, we may have to revisit the spectrum of the signals which are present at the input and the output of this mixer.